was called Human here on Kiwi. It is now 12 minutes past 9.
The Radio Wammo Breakfast.
Live from the New Scientist Labs, Janine Young, newscientist.com.
Is joining us in Melbourne, Janine Young. Hello to you. Good morning.
Good morning to you.
First up this morning, we're actually talking about a story, I suppose, that was published just a few days before the Christchurch earthquake, but it has been looking at earthquake prediction. What can you tell us about this?
Yeah, this was published on the 17th. It's important to say that this was not being published as an opportunistic kind of article. This was, done beforehand.
Yeah. Researchers
at the University of Grenoble have been looking at patterns for an earthquake that happened in Turkey, the Izmit earthquake in 1999. It was a 7.6 scale earthquake. And I should actually say that people that say that it's a 7.6 on the Richter scale, it's kind of like saying, 1.65 metres on the height scale. It's a really odd kind of thing. Anyway, This was a 7.6 scale earthquake, so it was a big one. It was huge. It killed 17,000 people. And of course, seismologists are interested in being able to find ways to be able to predict earthquakes. But if you can't predict them, because that is the holy grail, then you want to be able to at least get early warning to people. And the two, I might add, don't equate to the same thing. Having an hour's warning is not the same as having a couple of days. Evacuations take days. However, in looking at the patterns leading up to this very large earthquake, they found that there were very specific patterns in foreshocks, as they're called. So they were little tiny shakes in the earth that were happening before, about 45 minutes before this earthquake hit. It was a very substantial series of 5 shocks that people hadn't really noticed, but going through the records, they found that they had a very distinctive pattern. These 5 shocks had something called a P wave and an S wave. They're very distinctive patterns in the way they move through the earth. The P wave is the primary wave and gets there first because it travels fastest, and then the S wave is a slightly higher amplitude. These two were within 2.4 seconds of each other, and this was a really regular pattern for these 5 foreshocks. Now, the amplitudes were different, which means that their scale was different, so they were some were more stronger than others, but the waveforms were exactly the same, which is extremely unusual when it comes to earthquakes, because predictability and any kind of uniform behaviour is also very unusual. So they think, and this is only their best guess at the moment because they're still analysing data and they want to try and find out if it's going to happen in other earthquakes, is that up to about 45 minutes beforehand for very large earthquakes, and only very large earthquakes, they might be able to get some kind of indication that an earthquake is coming. The reason they think that it could only be very large earthquakes is because a lot of the monitoring that's gone on the San Andreas fault on the other side of the Pacific, again, as pretty much every New Zealander would know, you guys are on the Ring of Fire, and the San Andreas fault is on the other side of that, on the other side of the Pacific.
Yeah.
And in looking at that, they've not found the same patterns, and that's possibly the best monitored fault line in the world. So it's very likely that I think it was 1994 Parkfield earthquake, that was a magnitude 6 or the like, and that didn't have any foreshocks before it. So it's very possible that it's just the largest of earthquakes, and you want to know about all of them, but certainly the very large ones, particularly in areas like Turkey that probably don't have the same building codes as, say, Christchurch, or indeed Wellington. Everybody knows that Wellington is much more earthquake prone than Christchurch. In fact, I believe from what I've read this week that it's actually come as a real surprise because they didn't know that the fault line was even there up until last year.
That's right.
So having any kind of warning at all is going to be a big benefit if you can actually get that data manipulation done in real time, and if you can get that information out to people in real time and not cause mass panic. So at least early warning might be able to happen on some of the largest earthquakes on some fault lines. The problem is that we just don't know where they are at the moment and how reliable this kind of information will be.
Yeah, it's one of the sciences that seems to be where we're only just scratching the surface of, very just, right at the beginning of it. There's so little is known, and I suppose people who are affected by earthquakes just get really frustrated by that.
Is it any wonder? I mean, you want to know when the earth is going to shake around you and your earth is going to fall, your house is going to fall down around your ears. That's not surprising. The problem is that a lot of these fault lines have pieces of earth that have moved together for millions of years again, I think, and I'm not telling anyone in New Zealand anything they don't already know, I'm sure, that this fault line near Christchurch, the one that epicentre was near Littleton, hasn't moved for 10,000 years. And if you don't know it's there, you can't monitor it. And even if you are monitoring it and you're not getting any information off it because it hasn't moved, you can't predict it. You just have no way of knowing exactly what the Earth is going to do. These are systems that are dealing with massive amounts of energy across geological timescales. So to try and measure it in, half hour or hour or even day scales, that's not the way the Earth works.
No.
And so, yes, it's very frustrating, but there's only so much seismologists can do, and they are, frankly, doing the best they can, but it's not really enough, is it?
Well, that's right. Well, now on to something that humans can affect and can change, from earthquakes to nuclear waste, Janine.
Everything to do with the Earth this morning. Everybody knows that nuclear waste hangs around for quite a long time. It stays radioactive for about 250,000 years. That's a long time. So if you're actually going to put the waste into a nuclear waste dump in the ground, for example, you want to try and keep an idea on what's going on underneath the ground. Check its radiation levels, check it's not leaking, check there's no floodwater getting through. It's a serious business because for countries that do have nuclear power, then you need to be able to contain your waste. Researchers are now trying to find a way to get effectively a magnetic battery-operated system to try and get a check on it after 100 years. In the scale of 250,000 years, that's not a lot, but hey, let's not argue. Greenpeace, I might add, is not terribly impressed with this. They're kind of going, well, what about the other 99%?
Yeah.
They've got a point, but let's not dwell on the details.
Yeah.
This battery is a core. It's a rod. It's about 15 centimetres long of neodymium, which I must confess I'd not heard of, but I don't know everything. And it has a magnet at each end with another magnet in the middle that's held against an end that repels it. Everybody knows about magnets. If you try to push them together, the ends that repel won't stay together. But if you hold it in place, it will. With a copper core around it, that then means once you actually release the latch that holds that rod, then at the 100-year mark, and again, they've got to find a timer to be able to make sure that this is going to work. Once you release that latch, it sends it flying along the rod. Because it has a coil around it, it generates electricity in the coil. It's electromagnetism. Again, most people would know how that works from high school.
Yeah.
It's a very simple basis to this. So it crashes against the other and generates a electric current. That's just enough power to be able to run energy through sensors that can look at temperature and other really important critical factors, and then through radio signals transmit that back to the surface. So in principle, it's actually really simple, but then you've got the issue of the timer. You have the issue of being able to get the signal back to the surface. There are a few other practical issues that may come along and trip them up, but in principle, they actually have the idea of a kind of battery that's going to be able to give an indication of what's going on underground, because they can't use mains power, because if that fails, you're in real trouble. You also can't have any kind of conduit to the surface, because if you do, it's very likely floodwater is going to find its way down. Pardon me. And it also could let radioactive matter out, which is something you really don't want. So the system has to be sealed. So trying to find a way to get this information out safely is of importance. But again, you get an idea of what's going on in 100 years, but what about 100 years after that?
Well, that's right, and it really is the worst kind of time capsule, isn't it, for future generations? Like, here's a little note. Oh, look, here's something we left for you. Sorry about that. Just a little bit of rubbish. I'm sure you'll know what to do with it. It's pretty terrible.
Yes, technology will improve. You will work it out. You'll find a way.
Yeah.
It's a bit like, cryopreservation. Yeah, you'll find a way to thaw people out.
We don't know what to do with it. I'm sure you do. You'll be much smarter than us. Yeah. Oh, God. That's terrible. Well, there we go. Thanks very much, Janine. Cheers for that. Those stories in New Scientist magazine coming out next week, and, of course, also newscientist.com. And we'll see you next week. Thanks, Janine.
See you later.
Time now here on Kiwi, 22 minutes past 9.